Alright, so let's try to define what is the roughness inside a pipe. Usually the roughness is something that is identifiable only through the effects it causes on the resistance to motion, which means that you have a flow, you have a not uniform distribution of your roughness, and the presence of this roughness creates turbulence inside your flow. So, to study the roughness, first, moving from the discussion of smooth pipes, first they try to create a uniform roughness. This is the so-called Nicorat's experience, where Nicorat's creates tubes, and these tubes were made artificially rough by adhering to the wall of sand grains with a known diameter d. In this case, you observe that the tangential tension is a function of the diameter, the velocity ρ mu, but also it's a function of the roughness epsilon inside your pipe. So from the dimensional analysis, again, you can get this stuff. So it's tau 0 is equal to rho v to the power of 2 times a function lambda 1 of Reynolds and the known diameter. Basically, the two laws that describe this physical phenomenon, and they help you to get the friction factor, are the Prandtl von Karman's laws. One is the one that we saw before, remember this one in smooth pipes, and for turbulent flow in smooth pipes you get exactly the same law of the transition flow in smooth pipes. So it's exactly the same. Then, if we have a turbulent flow in rough pipes, something is changed, and experimentally it was demonstrated that after a certain value of Reynolds number, which is defined in this way, and we will see in the next, you get that your friction factor lambda right here is totally independent from Reynolds number, but it depends only on G over capital G. So it's the relative roughness, where little d is the known diameter. So basically, Nicorat's demonstrated that you can get the three different regimes of flow: laminar, transition, and turbulent. And when you are in laminar flow, you can exactly see that increasing Reynolds, it decreases the friction factor. But not only that, you don't have any dependence from the relative roughness. Then you have a drop on your line, and this drop is justified by the fact that you are considering uniform roughness. So basically there's also a problem of limit viscosity on your wall of the pipes. And after this drop, your curves become almost linear, rectilinear, and after one value of Reynolds, which is called a critical Reynolds number, you can get exactly this second Prandtl von Karman's laws, which is the one that defines the friction factor according only to the relative roughness of your flow. In particular, Reynolds number in critical values is defined as U star, which is the friction factor, the friction velocity, times G, again, over the kinematic viscosity, and this is equal to this stuff right here, and this is estimated as almost equal to 70. So, again, we say that this is true. So coming back to our scheme right now, this is equal to turbulent flow in smooth pipe. This law is valid for turbulent flow in smooth pipes, but again is also valid for transition flow in smooth pipes. And this stuff right here is valid for turbulent flow in rough pipes. But what happens if you don't have pipes where the roughness is uniform? And this is true for all the kind of pipes that you can find in commerce. Well, it happens that the roughness is not uniform. So basically, it happens that if you consider the straight of your roughness, you can find it's something like this. I try to explain it graphically on the paper. So basically, sorry, technical disease. So you have so you have that for uniform roughness, suppose something like this. This is the wall of your pipe, you have the roughness, and it's almost uniform. Your flow is coming, so you have the same right here and right there, because you have two walls. Suppose that the roughness is uniform again, you have the flow in this direction. Alright, so right here you have, really simplified, so I'm trying just to imagine, you have substrate which is characterized by a certain kind of viscosity. So basically your flow is moving in this direction, and it has a velocity which is maximum to the axis right now. Just simplify at all the problem, and then it decreases right here and right there. But if you have not a uniform roughness right here and right there, it comes that this turbulence is discontinuous, so you have something like this. So suppose that we have this one and that one and la 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 and so on. So basically this straight tends to decrease the diameter of your cross section of the flow. So basically it happens that it changes this substrate right here and right there. So basically it's something different, and usually you get a situation like this and not like that, because this one is an artificial situation, while this one is what you find in commerce, for example. And it's possible to observe, coming back to our scheme, that if the roughness is not uniform, it happens something like this. So you don't have anymore the drop, but you have that the commercial pipes, defined by the curves number B, are something that moves in this direction. So basically it follows the same discussion that we made before for uniform roughness, but it changes in this way. Usually to describe this situation, one can get the Colebrook-White law. So this Colebrook-White law sum all the things that we saw before for laminar flow, transition flow, and turbulent flow. Let's see what it says. It says that your friction factor is dependent from Reynolds number again, the friction factor, and epsilon over G. Epsilon is the roughness, and it's not uniform in this case, so you consider a factor right here which is called the relative roughness. If this term is almost equal to 0, you have in front of you the case of smooth pipes, so these terms right here disappears, and you get 1 over square lambda equal to minus 2 the logarithm of 2.51 over Reynolds times square lambda again, and not this stuff in this case. So you have Prandtl von Karman for transition flow or turbulent flow in smooth pipes. So it's the case of turbulent flow in smooth pipes. If you have the high values of Reynolds number, what happens again? That if this term is really high, then this ratio disappears and you get 1 over square lambda equal to minus 2 the logarithm of 1 over 3.71 times epsilon over d. So basically you have only the dependence on the relative roughness, which means that you are considering turbulent flow in rough pipes. So finally, in transition flow, what you can see is that your friction factor is dependent both from Reynolds number and to the relative roughness. So recalling just right now our scheme, we found this stuff. That okay, so we can just right now erase this and move this from this. Alright, then remember the scheme that we did before. So we get that this is true for transition flow. Then we get, and this was the Prandtl von Karman. Then we say that this law is also valid in turbulent flow plus smooth pipes. Then fourth case was the turbulent flow in rough pipes, and we say that again is valid Prandtl von Karman, that says that 1 over square lambda is equal to minus 2 the logarithm of 1 over 3.71 epsilon over d. So first resistance law, second resistance law, 1, 2, third resistance law, and finally to sum all this situation, last law that we see is experimental law, which is called the Collebrook-White, that says that 1 over square lambda is equal to minus 2 the logarithm of 2.51 over Reynolds times square lambda plus 1 over 3.71 epsilon over d. Hope this is almost clear. Alright, so to complete this discussion, let's talk about for a while of the experimental diagram, which is called the Moody Diagram. Basically, you have what you have seen before. So basically you have the laminar flow right here, which is characterized by a resistance law where you have 64 over Reynolds. Then there's a little, not very little, you have the transition region in this part of your diagram, and in particular right there there's a curve that defines the smooth pipe. So in this curve you have the Prandtl von Karman, where it's valid again transition and turbulent flow in smooth pipe. So right here you have the transition flow. This line defines the line where you can see the starting of the complete turbulence of the flow. So from this line on, you see only the turbulence flow. In this region right there, you see the transition flow, but inside this transition flow there is a particular situation characterized by the smooth pipes, where your turbulent flow is defined exactly as your transition flow by Prandtl von Karman's law. Again, you can see that in laminar flow your friction factor depends only on Reynolds number, while right here you see that you have the relative roughness, while in transition your curve defines something that is depending both from Reynolds and from the relative roughness, while in turbulence region you can see that increasing Reynolds number, you don't see any influence of friction on a friction factor, but your friction factor depends only on the relative roughness of your pipe. Alright. Okay, so let's try right now to define some practical formulas for water mains. Because, sorry, I forgot one thing. Usually, what the one does is the verification problem or project problem. So basically, when you are in front of a problem, you can have the aim of define the diameter of your problem, which means that you want to project a plant, for example, or otherwise you can define the volumetric discharge that is flowing inside your system. The second problem is the verification problem, and it means that you start just knowing the characteristics of your fluid, so you know the diameter of your pipe is roughness, you know the density and the dynamic viscosity of the fluid, but if you are lucky you also know, you should know the nature of your fluid, which means that you should know if the if the fluid is flow is laminar, transition or turbulent one. So usually what one does is to assume a value of Reynolds. So for example, assume in the beginning that your Reynolds number is defining a case of completely turbulence flow, which is the one that usually happens inside a pipe. Then you enter in a Moody diagram, you define, starting from this value of Reynolds number, and from the relative roughness you define the friction factor, and the friction factor allows you to compute J, so the hydraulic gradient from Darcy-Weisbach. Iteratively you can, once you have J, you can compute Q, the volumetric discharge, and then if you have Q you can remake the same things and see if Reynolds with this value of Q is the same or not of this one. So basically you go on and on, you make some iterations in your computations, and you see when the discrepancy between two different values of Reynolds number are higher or lower than a tolerance threshold that you have defined, of course, before. Alright, so right now let's see some practical formulas for water mains, because as we said, to cover all the fluid you can use again Darcy-Weisbach, and Darcy-Weisbach again told you that let's go back for a while, not here, that the hydraulic gradient is equal to lambda over g times v to the power of 2 over 2g, and is valid for every kind of flow. But what happens in water mains? Usually it happens that your flow is purely turbulent. So if this is true, you can, for example, you can define what is called the Chassis law. Chassis law say that your hydraulic gradient is equal to v to the power of 2 over a factor key is called to the power of 2 times the hydraulic radius. Alright, so this stuff is almost valid if you are considering common water mains. In particular, combining this law with Darcy-Weisbach, it is possible to demonstrate that K is equal to square 8g over lambda, so it is dependent from the friction factor again. To determine this key, there are some experimental laws that combine this key with the roughness index inside your pipe. So one of these is the Cutter law. Cutter says that K is equal to 100 over 1 plus m over square r, where m is a roughness index, and you can find it in different tables in practical manuals. The same is for basin. Well, we have to say that these two formulas are both experimental ones, but they are not so used, because the most used one is, of course, the Gauss-Strickler laws, which says that K is equal to Ks, so coefficient depending on the roughness, times the hydraulic radius to the power of 1 over 6. Ks is also equal to 1 over n, and n is called the Manning coefficient. Both of them are table, in particular, so Ks is equal to 1 over n. In particular, n is directly dependent on the roughness, that describes the roughness of your pipe. So if the roughness increases, then it means that n increases, but if n increases, Ks decreases, and it's what is called like this. Why? If n decreases, which means that the roughness of your pipe is small, well, if n is smaller, then Ks, it increases. So it's inverse proportion. Again, let's try to combine Gauss-Strickler law with Chassis law. Alright, so again, Chassis says that the hydraulic gradient only for purely turbulent flow is given by v to the power of 2 over ks to the power of 2 times r to the power, sorry, my fault, sorry, J, Z, sorry, says that J is equal to v to the power of 2 over k to the power of 2 times r. But recalling that Gauss-Strickler says that k is equal to ks times r to the power of 1 over 6, then we get that J is equal to v to the power of 2 over ks to the power of 2 times r to the power of 2 over 6 times r, v to the power of 2 over ks to the power of 2, 2 over 6 makes 1 over 3, so it's 1 over 3 plus 1, because you have to sum the exponent of this product, and it becomes r to the power of 4 over 3, which is exactly the laws that, combining Chesy with Gauss-Strickler, allows you to direct evaluate a project problem, because remember that you are considering in this formulation the permanent motion. Permanent motion means that your volumetric discharge is equal to the velocity times your cross-section area. So for example, if I'm substituting this stuff right here, what does it mean, this stuff? That Q is always constant and it's equal to the product of U times A. Also, this wants to say that since Q is constant, if the diameter inside your systems, so the cross-section of a pipe, is different, Q is constant, so V must be different, which means that if A increases, then the velocity decreases to maintain Q as a constant. While in the other way, if A decreases, then the velocity increases. So this was just a little reminder. Then substituting this stuff right here, you get that V is Q to the power of 2 over Ks to the power of 2 R to the power of 4 over 3 A to the power of 2. Alright, so you see that J is depending on Q, and in this way, if you know all the other stuff, you can evaluate Q and see if the Q is respected or not inside your problem.